In this video, we'll be going over how to implement Europa Clipper's Jupiter orbit insertion engine thrust visualization by using Cosmographia's ParticleSystem functionality, and we'll be going into detail of how all the parameters in the particle system affect how the plume looks. First, we need to find when the Jupiter orbit insertion burn happens using the published Europa Clipper trajectory data in the form of a spice kernel, which we can do by taking a look at the time history of Europa Clipper's velocity vector when arriving at Jupiter, and we can see the discontinuities here, which is marking the burn. And also note that this burn reduced Clipper's velocity with respect to Jupiter in order to capture into an elliptical orbit. Now, going into the Europa Clipper burn scene, we'll see how the engine plumes are defined in the spacecraft catalog. So here we give the engines a name centered at Europa Clipper and its trajectory and body frames to be fixed with Clipper's body frame because we are going to define the plume position and velocity directions with respect to Clipper's body fixed frame. And we define the plume to come from a fixed point with respect to Clipper's body. And note that these values are in kilometers and the axes are Clipper's body fixed axes. And here's the geometry where we define the particle system. The texture here is a JPEG image of a Gaussian distribution and is provided by Cosmographia's data and is included in this repository in the data directory, and it looks like this. And through trial and error, we found that the plume looked best when offset by 60 centimeters from when the fixed point center was previously defined. The size variable defines how far out the particles can be emitted in each direction, so we found that if we make the y and z too big, the particles come out with larger than desired non-axial velocity. The velocity variable is the nominal velocity vector of the particles, and this is nominal because the next setting controls how much the particles deviate from this vector. So in this case, if we decrease the velocity to 0.1, the plume is way too short, as we can see on the top engine here. And when it's 1.0, it's actually a bit too long for what we like, and up here is the nominal case. So the 0.5 number was determined just by trial and error. Again, velocity variation controls how much the particles can deviate from the nominal velocity vector, and with high variation, the plume looks less controlled, and lower is too straight along the velocity vector, so the plume appears to be perfectly still. Spawn rate controls the rate at which the particles are emitted, so if it's too low, the particles can be distinguished from each other and not look like a solid flow, as is shown here in the image. But note that there is a maximum of 200,000 particles per emitter allowed, and that is dictated by spawn rate and the lifetime of the particles. Lifetime is how long each particle is active in the scene. So if it's too low, particles don't get far enough away from the engine, which is the top engine. And if it's too high, particles get too far from the engine, which is the bottom engine. And note that the distance that the particles reach is dictated by lifetime and velocity. So for the same distance, one could increase the lifetime and decrease the velocity and vice versa. And these two values together are determined again by trial and error to see what looks best for the application. I haven't been able to exactly pin down what the trace value means, but from comparison, it seems that the larger the trace, the more elongated the plume is, as is shown at the top engine here. Start size and end size are how wide the plume is at its beginning and at its end. So here the top engine is showing what the plume looks like if the start size is greater than the end size, but in the case of engine plumes, we want the start size to be smaller than the end size. The colors are passed in as hex, where their corresponding number value is their relative brightness or thickness, and the order goes from start of the plume to end of the plume. So in the top engine, we can see these are the hex for red, green, blue. Same thing here, red, green, blue. But then we show how the different values, the different numerical values here, yield different results. And the start and end times define when the plumes should exist. But in actual reality, in the trajectory data, we see that the burn lasts about 100 seconds, but here it was set to a bit over an hour just for the effect of actually showing the plumes in the scene. And finally, the only difference between engine 0 here and engine 1 is its fixed point trajectory here. You can see that the y coordinate is negative here and positive here. So that's it for this video, and this was the final item on our list of tutorial videos to make. So let us know if you have any requests or suggestions about what else we should show for Cosmographia tutorials.